Okay, so we have given this this algorithm for the problem of RNA secondary structure, and as I said, this fits within the category of algorithms that we call dynamic programming. Okay, so the term programming here does not have to do with programming in real programming languages. This is just the name of this class of algorithms, and dynamic programming, as I said, it solves the problem. Certain problems, when we solve certain optimization problems, we observe that the optimal solution to the big problem can be obtained from optimal solutions to sub-problems. Like in this case here, the solution to the entire problem opt of 1n can be obtained from opt of 1 n minus 1 and opt of nt and 1 to t minus 1 and t plus 1 to t minus 1. So the solution to the bigger problem ij can be obtained from a solution to sub-problems that involve smaller sub-problems here. Okay, so when we look at dynamic programming, we have to have this property that the solution to the problem, the big problem, is obtained from solutions to sub-problems. And when we have this property, when we compute the solutions to sub-problems, we store them usually in a matrix. And when we come to solve the big problem, when we encounter these sub-problems, all we need to do, because they have been already computed, just look them up. So looking up this value, this value, this value, is O of 1 operation for each one of them. Of course, because we are doing this technique, the gain from dynamic programming comes in cases where the same subproblem needs to be computed over and over and over if we do recursive algorithm, for example. So if I get to a situation where the problem is solved from subproblems, but these subproblems do not overlap ever, in the sense that opt of 719 is solved once, opt of 720 is solved only once, or needed only once, then I'm not going to gain much. The gain I would get from this, if the same subproblem needs to be solved over and over and over, with dynamic programming, the way we do that, by solving it only once, storing it in a matrix, and every time we need to solve it again, all we do is just look up the value in the matrix. Okay? The other thing that we have to keep in mind, that the fact that I have written this kind of formula and this algorithm does not necessarily mean, or if I have dynamic programming, does not necessarily mean I have an efficient algorithm or what we mean polynomial time algorithm. For this to be polynomial, the sub-problems that we divide and solve has to be polynomial as well. Okay? Because if you have to solve, if the matrix has exponential size, there's nothing much you can do about it because you are filling the entire matrix. So usually the running time of a dynamic programming algorithm is dominated by the size of matrix, because, or the size of matrix, because we have the entries in the matrix. At least we have to fill out these entries in the matrix. Even if we do the simplest amount of computation, which is constant number of operations per entry, the number of entries in the matrix is going to give us a lower bound on the running time. Now, what is the running time of this algorithm? It's very simple actually to analyze. This loop here is on the order of n, right? N minus 5, it is order of n. This here is also on the order of n, because in the worst case, n is 5, and this is going to go from 1 to n minus 5. This is O of 1. Here, this is going to be O of 1. Of course, this is O of 1. O of 1, the addition is O of 1. But there's this t that is ranging. If I'm looking again, in the worst case, at position n, t could be any of these positions here. So in the worst case, it is O of n. So this t, we might, in the worst case, be looking at O of n values. So this can be O of n. So O of n, this is nested within it. This is nested within this. So this algorithm is on the order of n cubed. Okay? And this is much better than trying a brute force approach that would have tried, for example, let's look at every possible way of pairing indices in the RNA secondary structure and then check feasibility, and then find the one with the maximum number. Okay? And if you want to think about, is this faster than the recursive algorithm, I highly encourage you to implement this as in dynamic programming using a matrix. Just implement this using a recursive version, where this opt is the name of the function instead of a matrix. So you are calling the function here every time, and run them and look at the running time of these two algorithms and see which one is going to be faster. Of course, with dynamic programming, when we are looking at dynamic programming implementation, there is an issue always with the memory, because we have to be building that matrix. Okay? Usually the memory is not a big deal when we are looking at small strings, because it is, in this case, it's going to be on the order of n squared. But if n gets very, very large, the dynamic programming approaches start suffering because of the memory issue. They are still efficient in terms of time, but the amount of memory they need to store becomes very large, and that becomes the bottleneck. Okay? One final word about this algorithm for RNA secondary structure and with respect to dynamic programming is, remember that the biologist was not interested in a number. The biologist didn't tell me, it didn't ask me to give them the number of pairs that are going to match. The biologist wanted the actual pairs because they wanted the actual structure. So how would I get the actual pairs themselves rather than just the number? Because when I say return opt of 1n, this can be like the number 5. But the biologist is interested not in 5. The biologist is interested in the 5 pairs that I produced. That's very easy to obtain if you think about this algorithm carefully. When you look at opt1n, it's either the max of this or this. If this is the value that's giving us the max, then we know that n is not part of the solution. We repeat the exercise now on 1 to n minus 1. If this is the part that gives us the solution, then we find the t that is maximizing this value. If t is, let's say, 7, and n is 100, then we tell the biologist 7 and 100 are going to be one of the pairs. Then we repeat the exercise and find what are the other pairs. Okay? So this is a technique that's called backtracking. When we compute the answer using dynamic programming, usually we are computing a number that is related to the solution, which is usually the optimality score. Here it's the maximum number of pairs, or something like that in other algorithms. So usually dynamic programming algorithms are implemented in such a way that the matrix is containing, the entries are containing the optimality score. But using the traceback technique, we can find the actual solution, not just the score of it. Okay? And again, here by just the traceback is you go from the, remember that the matrix we built, 1n was here. This is opt of 1n. We start from this entry here. We start from this entry and start doing a traceback to find the actual pairs that form the RNA secondary structure.